Bismillahirrahmanirrahim. In the last lecture, we saw that if we are studying the effects of a drug, the treatment group and the control group must be matched. If they are not, then some other factor which differs between the treatment group and the control group might be the cause of the difference in the outcomes. And this phenomena is called confounding, and we will study one approach to the solution of this problem, which is called randomization. So we divide the group of patients into two groups. One is given the treatment, the other one is left without treatment. And we look at the average outcome of the treatment group and the average outcome of the control group and look at the difference. And presumably, this difference should be due to the treatment by the drug. But there might be other factors which influence this outcome. And if these other factors are different between the treatment group and the control group, then these factors might be the cause of the difference in the outcomes. So how do we take care of this? How do we make sure that the treatment group and the control group are different only due to the treatment and not due to any other factor? This requires some thought, and that's basically what we are going to do in this lecture. Consider as a thought experiment a case where only one factor can affect the outcome, and let's suppose that is gender. And so the females have different response to the drug and the males have different response to the drug. So if we mix up the two groups, if one group has more females and the other group has more males, then the treatment and the control outcomes will be different. But the difference will be partly due to the drug and partly due to the gender balance. So how can we solve this problem? There is one simple solution which is called conditioning. Just separate the two groups, study the females separately and study the males separately. So then if we just look at the female response or the male response and look at the treatment and control difference, we will get the difference for the particular group under study, but that may not be very helpful because we want to generalize this response to the population as a whole. So this is the question: how can we make sure that the difference in our study generalizes to the population as a whole? And basically the answer is that the females in our study group and our experiment must be representative of females in the general population. So how can we make sure of this? And if we don't try to ensure this, how much difference will this make? So these are some of the questions that we will discuss in this lecture. Instead of conditioning, there is another method to handle the problem of confounding, and that is to make sure that the balance of females and males within control group and treatment group is the same. So this time we don't want to analyze the female response and the male response separately. We just want to make sure this factor doesn't matter by keeping the same mix in the control group and in the treatment group. So this can certainly be done, but then the question arises that the mix that we have of males and females in our experiment, does this reflect the mix in the population in general? Also, it is possible that all of the females have somewhat different responses. So some of the females are more sensitive to the drug and others are less. So is it possible that in our experiment we have picked a subgroup of females for the experiment which is different from the general population? It was the brilliance of Sir Ronald Fisher to come up with a solution to the problem which now seems routine and clear, but at that time it seemed very unusual and different. And that was that you pick the sample at random from the available population. There is a general theorem of probability theory which we will present here in a heuristic form. And suppose that I have a very large sample, millions of people in the population. From this, I need to pick a random sample. So a random sample is one in which every one of the million people have an equal chance, 1 over 1 million, of being chosen in the sample. If I can somehow arrange to get a random sample, then in some sense everyone is represented because everyone had a chance to be there. So if we pick a random sample of 1,000, then there is a probability theorem that let f be any factor like gender or some genetic characteristic, any characteristic, and suppose that the characteristic is present in the overall population, maybe it's 67% for example, then in my random sample of 1,000, approximately 67% of the people in the random sample will have the same characteristics. So the proportion of people with an unknown factor within the random sample will be close to the proportion in the total population. So this is one of the important theorems of probability theory, which tells us that if I pick a random sample, then it will be representative of the population even with respect to unknown factors. So this is the basis of random sampling. That is why when we are studying drug treatments, the gold standard is considered the randomized experiment. It cannot always be done for reasons that we will discuss later. But basically, if we choose both the treatment and the control group as random samples from the population, then both of them will match the population, and then of course they will also match each other. And so the issue of being representative of the population will be correct. So basically, if there is a difference between the treatment and the control group in terms of the average outcome, this difference will also translate to the population as a whole, because both treatment and control are representative of the population in general. There is a warning that if there are subgroups in the population which have different responses, one of the groups is very strongly affected by the drug, the other is adversely affected, this will not show up in the randomized experiment because we are just averaging over the whole group. So the idea that there may be different subgroups with very different responses, this will not be covered, but the total average of the group as a population as a whole will be correctly represented by the sample. Now we just present some examples of the randomized sampling and discuss some real-world cases. So in the 1950s, the Salk vaccine was discovered, and doctors wanted to know how effective this is in terms of preventing polio. So just to give some information, polio is an epidemic disease, and it varies, fluctuates quite a lot. In 52, there were 60,000 cases. Next year, there were 20. Next year, there were 80. Next year, there were 45. These are just some numbers which are given to give you an example. These are not the true numbers. So with this kind of variation, suppose that we give the polio vaccine to all the children in 1956 after these 4 years. What would we learn from the outcome? Well, suppose that there were very few cases, like 10,000. This is less than all of the 4 years. Would that mean that the vaccine had worked? We can't be sure, because maybe like it went down without any change from 60,000 to 20,000. So it could have gone from 45,000 to 10,000 just because polio didn't spread that year and the vaccine had no effect. Or even if it goes up to 90,000, which is doubling of cases, again, we can't be sure if it's due to the vaccine. So basically, the issue is that whenever we make a study, we have to have some benchmark. This is what happens with the vaccine, and this is what happens without the vaccine. At this point, we have 90,000 cases with the vaccine, but what would have happened without the vaccine, we don't know. So we don't have a benchmark, we don't have a baseline, so we can't say anything from such a study. This is very important to emphasize because comparisons are made without benchmarks quite often, and as statisticians we need to learn to recognize that. So for example, consider the statement that Pakistan has made tremendous progress in improving infant mortality. In 1960 it was 120 cases per thousand, and in 2000 in 40 years we have gone down to 60 per 1000. We have halved the infant mortality rate, and this is a tremendous achievement. Is this a true statement or is it a false statement? The answer is we can't say because no benchmark has been provided. Some countries did better than this over the same time period, other countries did worse. So it's impossible to say if this is good or bad. And if we choose the benchmark, if I choose a country which has done worse, then I can say, look, this is better than country X. Or I can make it look bad by comparing to another country which had higher infant mortality in 1960 and lower than us in 2000. So we can make it look good or bad by choosing the benchmark. There is a natural benchmark, and we can look at the rank of Pakistan among countries. And if we look at that, it turns out that Pakistan is around 75th percentile. It is in the bottom, the worst 25%, and it has remained roughly stable around that percentile. So basically, when we compare it to how other countries have been doing, Pakistan has been doing neither well nor better. It has maintained its place. But there are many other kinds of comparisons which could be made. Coming back to polio, we look at the National Foundation for Infantile Paralysis, the technical name for polio. And this did a huge study in which many children in grade 2 all across the nation were chosen as the treatment group, and grades 1 and 3 were chosen as the controls. So this was an effort to create comparability. Grade 2 children should match 1 and 3 on most aspects, and so it was thought that this would create balance between the treatment group and the control group. But there was one complication, and that polio was an experimental drug. We couldn't give it to everyone forcibly. So in grade 2, some of the parents consented to receive the polio drug, while the others did not. So this table shows the outcomes. In grade 2, 225,000 students were the treatment group, and among these there were 56 polio cases, which reduces to a rate of 25 per 100,000. Grades 1 and 3 had 725,000 students and 392 polio cases, which is about double the rate at 54. And also the grade 2 no consent cases, there were 125,000, and they had about 55 cases, which is a rate of 44 per 100,000. From that data, it looks like the drug worked. In the treatment group, we had 25 per 100,000. In the control group, we had 44. So it seems like 54. It seems like the treatment reduced the polio cases from 54 to 25. So basically, the number of polio cases was cut in half. But then the question again is, are the treatment group and the control group similar with respect to unknown factors? And one of the unknown factors is immunity. Some children have higher immunity levels to polio, and others have lower immunity and lower resistance. So if the treatment group and the control group are balanced in terms of immunity, then we can attribute the difference in the outcome to the treatment. But if they are not balanced, then we cannot be sure about this. Where is the issue of consent? In the grade 2, only those people who consented were given the treatment, and those who did not consent were not treated. Now, if we look at the grade 2 no consent group, the polio rate is 44 cases per 100,000, which is different from the 54 which we see in the grades 1 and 3 control group. So there is something strange. The no consent group has a lower polio rate than the control group. Why is that? Neither of these two groups received the drug. The no consent group did not receive the drug, and the grades 1 and 2 groups did not receive the drug. So it seems that offhand, it doesn't seem likely that not consenting to the drug would have any effect on the outcomes. But it does seem that way from the data. And it turns out that when you analyze the data, you find that people who do not consent to receive treatment are generally low income. And in the low income people, you have less hygienic environments, which means that the exposure of the children to polio is greater, and that creates greater immunity. So we can fix this problem by trying to match incomes across the control group and the treatment group. So, but that would take care of the known factors, and there might be other factors which are unknown, which cause a difference, which we have not controlled for. So the real solution to this is randomization. So this study was repeated in a randomized double-blind control study. At the first step, the experimental group was divided into consenters and non-consenters, and the experiment was only conducted on the people who consented. So among the people who consented, these were divided into the treatment and control group. So now both the treatment and control group are equal on this factor of consent. Now when the random assignment was done to both treatment and control, then this creates a balance. Both of the groups are now balanced in terms of all unknown factors. And in this study, the treatment group had a rate of polio of 28 per 100,000, and the control group had 71. So this showed that there was a huge difference, about 43 percentage points between treatment and control. The polio vaccine is very effective in reducing the number of cases of polio. There is one very interesting fine point. The treatment and control group division itself creates a division, even though the randomization does not. And how can that matter for the treatment? Well, there is something called the placebo effect. If somebody believes that he is being treated for a drug, he is likely to recover from the disease, because there is some inborn psychological mechanism that the body, if it feels that it can heal the body, then it works to do so. So to prevent that from happening, all of the children in the study were given polio drops, but some of these were fake and some of these were real. All of them believed that they were receiving some treatment. So this is called blinding the subjects. Also, the doctors were also not told who has been treated by polio and who has not, because the doctors can actually, at the end, they are called upon to classify, does this student have polio or does it not? So if the doctors know that somebody has received the polio vaccine, then in cases where there is ambiguity, where you're not sure whether or not the child has polio, the doctor might classify non-polio, someone who has received the vaccine, and as polio, someone who has not received the vaccine, thereby creating a bias. So if the doctor doesn't know, then this bias will not exist. So this is called double blinding. Both the experimenter and the subject, neither of them know who has been treated and who has not. We'll look at some more cases of randomization and its effects. So one of the very famous cases is the Literary Digest. In 1936, the USA was suffering from the aftermath of the Great Depression. There was huge amounts of unemployment, and FDR, or Franklin Delano Roosevelt, was running on a platform where he said he would run deficits in order to help the people, and the government would spend money which they didn't have. As opposed to him, Landon was a Republican, and he was running on a platform of balancing budgets. He said that we should not be spending so much money. Literary Digest predicted an overwhelming victory for Landon based on the largest poll ever conducted. They polled all of their readers, and 2.5 million of their readers responded. And Literary Digest was a prestigious magazine, and it had successfully predicted results since 1916. But in this poll, Literary Digest went hugely wrong. They predicted that Roosevelt would get 43%, but he actually got 60%. This was a huge error, and basically Literary Digest suffered from huge loss of prestige, and they went bankrupt as a result. About the same time, Gallup, the famous Gallup poll, was starting up with his business of taking random samples, and he took a random sample of about 50,000 people, much less than the 2.5 million of Literary Digest, and he predicted a victory for Roosevelt. His prediction was that Roosevelt would get 54% of the vote, and the actual vote was 62%, so there was a large 8% error, but the result was right. More interestingly, Gallup took a random sample of 3,000 from the Literary Digest readers, and he predicted that Literary Digest would predict 44% vote for FDR, and actually Literary Digest predicted 43%. So there are three questions. Why did Literary Digest make such a huge error? How did Gallup make an accurate prediction of the Literary Digest results? And why did he make such a big mistake on the overall election results, even though he got it right? So there is a simple answer. The Literary Digest huge error was because the readers of Literary Digest were not a random sample from the population. There was a huge over-representation of the wealthier and more educated people, and that's where the Republicans are. So their poll was heavily biased in favor of Republicans, which is why they went wrong. Now, how did Gallup, even though he got the right result, why did he make such a big mistake of about 8% with a sample of 50,000? Well, there are two problems here. First is that random sampling itself is hugely difficult because you have to ensure that every member of the population who is going to vote has an equal chance of being in the poll. Not having a list of all the population, not knowing who's going to vote and who's not going to vote, you can only achieve this very approximately. In addition, there is a huge problem that at the time that you're polling, people don't even know whether or not they will actually go to the polls and vote. So you have to catch those people who are going to vote and differentiate them from those who are not going to vote. And this turns out to be a difficult problem. So Gallup's error was large. Actually, in later years, Gallup's organization improved and perfected their methods, and now they usually use fairly small samples from 3,000 to 4,000, and they get fairly accurate results. The third question was that how did Gallup predict Literary Digest results so accurately? Well, for that case, they had the complete list of the readers of Literary Digest, so it was possible to accurately create a random sample of 3,000 readers. And one very surprising result is that when you're looking for accuracy of the random sample, it is not the size of the population. It can be million or it can be billion. The accuracy only depends on the size of the random sample. So 3,000 is sufficient to get a fairly accurate prediction in this case. It doesn't matter how many total readers there are. Just to explain how things can go wrong, we will discuss some of the wrong methods for choosing controls which don't involve randomization, and we'll look at some real-world studies and show how they got the results wrong with serious consequences. So these examples are taken from Friedman, Pusani, and Purvis' book on statistics, and this example discusses a certain difficult and complicated type of surgery. And table 2 shows studies of 51 studies were done on this surgery, and there are 3 types of surgeries. No controls, you just do the experiment and you look at the results, and you don't have any benchmark for comparison. So there were, among these studies, 24 of them showed a lot of enthusiasm for the surgery. 7 of them were moderately in favor, and there was 1 study with no controls which said, no, this is not a good idea. The second type of study had benchmarks, had controls, but they were not randomized. Again, in these studies, 10 of them were enthusiastic in favor of Portacaval shunt. 3 of them were moderately in favor, and only 2 were not in favor. But when you look at the 4 randomized controls study, then 3 of them are against, not in favor, and 1 of them was moderately in favor of the surgery. So how these experiments are done, there is a classification given here which explains why these results were obtained. Why did the randomized control studies come to almost the opposite conclusion of the non-randomized studies? So if you have an experiment, it has to be controlled. So uncontrolled experiments are not experiments at all. Without a benchmark, you can't do comparisons. Now, when it comes to controlled, there are 2 types. You can either randomize or you can not randomize. So when you don't have randomized studies, then what doctors typically do is that they look at the patients and they look at those who are eligible for surgery. They have to be healthier so as to survive the side effects of surgery. And generally the sicker patients, the ones who cannot be operated upon, are left as controls. So there is an automatic bias in favor of the surgery because the healthier patients, the one who can actually tolerate surgery, are selected for surgery. As opposed to this, in randomized study, you first look at the eligible patients. So all of them are matched in the level of healthiness. All of them are eligible for surgery. But then among those eligible for surgery, you leave out some of them as controls. And so that makes for a better match between the controls and the operated. And you can see this process in table 3, because if you look at the randomized trials, then the 3-year survival rates in the surgery groups and in the control groups are the same, which shows that the surgery had no effect, no additional effect, and both of the patients with surgery and without surgery had roughly 60% survival rates in the 3-year period, so they were equally healthy. But when you look at the non-randomized controls, you find that the people who had surgery had 60% survival, but the controls who did not have surgery have only 45% survival. So these controls are different from the controls in the randomized experiment. Notice that both of the randomized and the non-randomized controls, they didn't have surgery. So the reduction from 60% to 45% is not the effect of surgery, is the effect of being in the control group. So basically this shows that the control groups in the non-randomized experiments were sicker than the ones who were chosen for surgery. And because of this, the difference that occurs in the mortality rate is not due to the surgery, it's due to the way that the controls were chosen as being the sicker. Again, this shows another type of control which is used, which is called historical control. You look at what has happened in the past in this, and you and you can use the history of the procedure as the benchmark or the control for what you do now. So there are 4 therapies which are studied. This is a study of studies, coronary bypass, and you see that in the randomized controls, only 1 of them is in favor, and in 7 of them are against. Whereas if you look at historical controls, then 16 of them say that this is a great surgery, and only 5 of them are against. And similarly, 4 different procedures. In all of them, the historical control studies are coming to the opposite results of the randomized control studies. And you can see the same phenomena at work, that it is not the advantage to the surgery or the treatment doesn't come from the difference between the difference due to the surgery. If you look at the table 5, you see that it is the historical controls who are worse than all the rest. And so basically the historical controls are doing badly compared to the people who receive the treatment. And why is that? Well, there can be general improvements in treatment of patients over time, and that could lead to a general improvement in the survival rates. And so when you look at the current outcomes for surgery and compare it to what has been happening in the past to those people without surgery, there is a bias introduced by the improvements in medical methods. And in particular, the book Friedman goes on to make the point that the DES surgery, in which the doctors ignored, there were 5 studies which showed strong favorable effects and 3 studies which did not show good effects, 3 randomized studies. The doctors ignored the differences between randomized and historical, and that resulted in a medical tragedy, because actually this DES treatment was quite harmful in the long term, and that was not discovered until late when the DES was banned as a treatment. So we can summarize this whole discussion. There are studies of surgeries or treatments by drugs. Some of these are no controls. These are useless because there is no benchmark for comparison, and these do not qualify as experiments. But when you have a control study, then you have some people who were treated and some people who were not. These are called controls. And now the controls can be historical, what used to happen in the past, or contemporaneous, currently what is happening. So as we have seen, historical controls introduce a huge bias. But even when you have contemporaneous controls, there are some which are called observational studies. You just look at what happened. Or you create the control group and the treatment group, so you have more control. So the observational studies are quite different from the controlled experiments. When you have controlled experiments, you have some control over who you're choosing for control and who you're choosing for treatment, and you can try to match the controls to the treatments even when you don't have randomization. Or if you have randomization, then you can create a match between the control and the treatment by randomization, which is very safe and effective. When you don't have randomization, and there are cases like smoking where you can't really randomize, you can't force people to smoke. So in that case, you have to match on other factors. Okay, and so this is the final slide, and basically the way that we want to find about causal effects relies on exogeneity. If I can make a change which is not influenced by anything under any variable under the study, that is exogeneity. And so if the variable changes at my will, I choose to throw a switch or to pull it back, then only my decision matters, nothing else matters. That's called exogenous. And so then I can study the effects of this exogenous variable. Free will creates an exogenous variable. That's when the experimenter is setting the lever of the machine at some value and seeing what happens as a result. Randomization also creates an exogenous variable. If I flip a coin and according to the heads or tails, I decide who will get what treatment, then that decision is also exogenous. It is not influenced by anything else. And when you have exogenous variables, then you can easily tell the effect of this because it's not confused or confounded with other factors. But if you don't randomize, the treatment and control group are selected by processes which we don't know about, then there can be differences in this treatment and control which are not under our control, which are other factors which are called confounding factors. Existence of confounding factors can lead to serious results, serious errors, and we can often make mistakes in, you see, when history is actually happening, then lots of things are changing, and we can say, oh, this happened due to such and such factor, whereas in fact it is due to some other factor which has also changed. This is a very common problem, and there is no easy solution to this problem.